They are starting. Wolfram's going to take a lot of yeah, Wolfram will give us at least I don't know. He has a lot of wants to share. So you have time. No, you won't be. You won't be. They're all coming with Yep, I got bored. I usually hate them after a while because it's like in my way, but
I know it's really good. It's like a few people might play. It's a nice, very nice movie.
when? Today? Already? Wow.
So, is it... How do I get this link?
Say it again?
How do I get this link to the...
It should be on the agenda. So let's get away from it because they can't hear us. Live is a little
No, it's Thursday. He's actually out. Wait, let's use the mic.
Amia, can you come to the front? Amia?
Let me say his last name. Amir Palinka.
Amia Valenka, can you come to the front? Amia Valenka? Amia, if you're here, please come to the front.
Hi.
I think I saw you. I didn't know who was who.
Great, yeah, Jeremy, busy man. Thanks so much for coming. That will be a podium. I see you back to that.
No, I'm just like, I'm done. Okay, and that'll be roughly like.
I think I'll just it's okay, I promise. I'll book you.
Alright, sounds good.
Sounds
Yeah, we're going to Singapore, London. Pretty great. Oh, no, yeah. Well, what kind of? So companies make agencies. Products still don't. Yeah. High agency company. High agency insurance. Yeah. It's been great. You can always use it back home, AGI home. I'm like interested. I think I learned to hate science. So I really like. I love this book called Structures of Science. also very curious to have this people arrive. That's so yeah, like I'm very curious about the discovery process. It's also like it's kind of wacky to me that like I'm still 60 seconds like they kind of tendency to pull it out.
Micron Ventures.
I did. On Potterful, I linked it because it's related. This one should have a chat with you know Potterful?
I've never seen it.
I shared it. All good? Staying away from
I said we're dealing with two overlapping conferences. That's what we're talking about. Completely different conference within I'm not in management quality. I've got a great view of it in Boston Square.
Welcome to the AI for Physics Hackathon! Woo! It's truly a joy to be with you and what I see as a very special time. There are phenomenal technologies and massive overhang that allow you and me to create fantastic new physics-facing projects. Everything from the mathematical tools akin to AlphaProof, about which we'll hear to talk today, to the very practical, high-quality simulations that allow us to optimize systems. Silence, please. So we brought together a fantastic crew. We have a few talks, the first from Stephen Wolfram, who for me is an inspiration when it comes to the theory of everything. There's this question of computational physics, a question which may be answered by cellular automata or by perhaps some new conception of high quality world simulation that you invent here today. And my intention is really to create a context where the fulfillment of the highest dreams of artificial intelligence, which are typically framed as understanding the fundamental nature of our reality, are brought to fruition. So let us christen the first AI for Physics Hackathon talk, Stephen Wolfram, with a warm round of applause.
Thanks. Well, let's see. I am not in my natural habitat this afternoon, although I have a great view of the Boston skyline behind me. I thought what I would do is talk a little bit about our efforts to kind of understand the machine code of physics, the machine code of the universe, and give you some ideas for sort of how you might be able to contribute to that. So maybe I should start off with sort of an important piece of intuition, which is a thing that I discovered, I don't know, 40 years ago now, which is simple computational rules can do very complicated things. So for instance, we can do sort of the characteristic computer experiment, which I first did like 40 years ago on this. We could just say, let's say we make a cellular automaton, maybe make this a bit bigger. And I'm using Wolfram language to do all of this. That's kind of the platform that I've built to let me discover things in science, and happily it's let millions of other people also discover things in science. So the idea here is we've got a very simple rule, just a line of black and white cells. At each step, it's specifying how to color the next cell down. And we could say, make a picture of what we get by running those rules, starting off with just one black cell, running them, let's say, for 40 steps. That's what we get, just a simple pattern like that. Well, we can change the rule here. Let's say we change it to this rule here. We can run that again, and we'll get a slightly more elaborate pattern. Continue that a while longer, we get a more elaborate pattern. Okay, big question is, in this sort of universe of possible artificial universes, we can think of this cellular automaton as kind of defining a very minimal artificial universe. Let's say that we want to look at all possible kind of minimal artificial universes of this type. Let's say we just run them for 40 steps or something, and we just do that. There are 256 of these things. Let's just run them all. Okay, so what we're seeing here is kind of what these kind of minimal artificial universes would do if we run them. And so what we'll see is many of them do very boring things. Some of them make these nested patterns, but at least one of them, this is rule 30, does something more elaborate. This is kind of my all-time favorite science discovery. We look at the rule here, we can say there's rule 30, let's run it, this is what it does. And the big surprise is that even though that rule is very simple, the behavior that it produces, even starting with just one black cell, is really complicated. So for example, the center column here seems for all practical purposes completely random. So as soon as one's seen this kind of behavior, an obvious question to ask is, well, is this how our whole universe works? Does our whole universe have some simple underlying rule that it's just running to produce everything that we see in the universe? So I was wondering about that. Oops, I'm about to, sorry, I have to, I hijacked a room at another conference that I'm supposed to be giving a talk at very soon, so I might get interrupted from time to time. So anyway, the question is, what's the raw material from which one can build physics? And one of the things we know about physics is that space exists, time exists, and so on. What's underneath space as we know it? In a cellular automaton, you have this rigid array of cells already laid out in space. You've already defined what space is like. So a thing that I first thought about this in the early 1990s, is what sort of a more flexible medium from which you can build space and everything in it. And what ended up with at that time was the idea of graphs, networks, Now, 5 years ago, we started our physics project, Wolfram Physics Project, and so the foundation of that is the idea that everything in the universe, space and everything in it, is just formed from a giant network of elements we can think of as atoms of space, and the only thing we know about those atoms of space is how they're related to each other. So let's take a look at something like that. By the way, I will say that the thing that you can look at everything I've written about this. It's on the Physics Project website. But an important fact to know is that anytime you see a picture in one of these things that I've written, you can click that picture, you get the code, you can just lots of other so automata there. You can just run that code, and hopefully you can just run that code, and you can reproduce what was in the thing I wrote. And so in terms of sort of following up on this, a really good place to start is look at any of these things I've written and click any picture, you get the code, and you can modify it and run it how you want it to run. Okay, so big sort of idea is everything in the universe is just made of space, and space is this thing that is sort of that is a collection of atoms of space related with relations between them. So, by the way, sort of the sort of back in antiquity, people were arguing at length, is the universe really discrete, made of atoms, or is it continuous, made of things that flow and so on? And that argument continued until the end of the 19th century, when it finally became clear that at least matter is discrete. And then it became clear that you can think of light as being made of photons, also discrete. At the time, beginning part of the 20th century, most people believed that space was discrete too. But nobody could actually make that work. And all the sort of greats of physics were saying, yes, in the end, space will turn out to be discrete, but we don't have the tools to understand how to do this now. 100 years later, we do have the tools. And we've made amazing progress by thinking about the universe as being built up from this kind of discrete structure. So how does this work? Well, let's say we have something like this. It's a very simple graph. And let's say that we have a rule that says how we take this graph and rewrite it. So we're saying here, those things that you see on the left, you can each piece here is a relation between these atoms of space, so to speak. And this says whenever you have a relation that looks like this, you should transform it like that. So what happens if we do something a little bit like the cellular automaton, but now we're dealing with this hypergraph? What happens if we just run things? So let's say we start from this initial state, and we keep running, and we build up this complicated structure. So the idea is that complicated structure that you build up is the structure of space and of everything in space, all the particles, black holes, whatever else. So you can kind of see why that might be plausible by taking a look. Let's take a look at an example like this one. This is another rule. Let's run that rule. It keeps on building up like this. Turns out what you get by running that rule is something that looks like this. It's kind of a thing that looks like a two-dimensional lump of something like space. And so, you can run different rules. Here's another one. It builds up something that looks like kind of a two-dimensional piece of sort of curved space. Well, one feature of this is in these models, you don't even know what the dimension of space is. The large-scale limit of all of these rewriting processes, of all of these updates, gives you the structure. You don't necessarily know what dimension that structure has. But you can kind of guess, you can work that out by saying, look at the graph we've got, start from a given node in the graph, keep building up this kind of ball that gets bigger and bigger, and ask how many nodes are there inside that ball. If a distance r, there are about r to the d nodes, you say this is roughly d-dimensional space. Well, you can do this kind of thing, and turns out that the correction term for that volume of the ball turns out to be proportional to the Ricci scalar curvature of the effective space. And so that kind of gives you the first hint of some connection between things that one is used to from things like general relativity, the theory of gravity, and this kind of model. So in any case, the main bottom line is that if you use this kind of model and you just say, well, what's happening is all these rewrites of this underlying hypergraph, the things I showed you so far were just graphs, but in general, you can have not just two nodes related by an edge, but any number of nodes related by a hyperedge. And in any case, the thing you discover is it's a little bit like the following. When you think about a fluid like water, at the lowest level, it consists of a bunch of discrete molecules bouncing around. But we know that on a large scale, the equations that specify what the fluid is going to do are the Navier-Stokes equations for fluid flow. So the question is, when you have this hypergraph rewriting system, what are the large scale equations that determine what the behavior of the system will be like? And it turns out, this is something I discovered in the 1990s, big fact is it turns out that the equations you get are the Einstein equations, the standard equations for the structure of space-time. So that's kind of a good start. But in any case, you can then go on and you can look at, let's see if I can find this. You can look at kind of how the universe, let me just see here. This is, hopefully, let's see if this works. Yeah, so this is kind of what the very beginning of the universe might be like in a model like this, showing progressive rewriting of this graph as it builds up kind of the structure of space and everything in space. If you keep running a lot longer, someplace in the universe, you might see something like this. This is two very tiny black holes that are now being updated according to these microscopic rules of this hypergraph, and you'll see these two black holes will eventually merge, and they'll produce some gravitational radiation, which turns out to seem like it follows what we expect from general relativity. Many details of this are complicated. Okay, that's the story of how you reproduce kind of the structure of space-time. It's at least a very abbreviated story of that. Another big feature of physics is quantum mechanics. The big thing that happens in these models is when you do the rewriting of these graphs, actually there are many possible rewritings that you might do. So instead of there just being one rewriting, there will be multiple rewritings that happen, and you build up this whole structure of these many different paths of history. And that story ends up being a story of quantum mechanics, and this whole purple thing that you see here is what we call a branchial graph, which is kind of the thing that relates the different sort of threads of history that we get to perceive in quantum mechanics. So anyway, what can one do with this? Well, for example, one thing one can do is just look at hypergraph rewriting, and you can start asking, can you find rules for hypergraph rewriting that have particular properties? And I've looked at a certain amount of that. We have a kind of registry of notable universes that contains some of the kinds of things you can find. Let's see if I can pull that up. Here, this is our registry of notable universes, but there are many more universes to be found. And then there are questions about how do you construct. So there's a certain amount of ruleology, as I would call it, of just studying these rules abstractly and seeing what they do, both rules that are based on graphs. You can also look at rules based on other kinds of things, but the rules based on graphs have sort of this most direct connection to physics, to fundamental physics. They're also a big effort that we have is to try and build up sort of all of mathematics from hypergraphs. So usually when you think about space, people assume that space is continuous. That's been sort of the assumption for the last 100 years. And there's a whole mathematical theory which ends with things like differential geometry and so on about the way that continuous space works. In standard continuous space, you kind of zoom in, closely enough on a manifold, and you'll see Euclidean space. But in our models, in these hypergraphs, you don't see that. You see some hypergraph that's rewriting. And so we're trying to build this thing we're calling infrageometry, which is kind of a rebuilding of all of geometry and then all of calculus, based not on manifolds and continuous space, but on these hypergraphs and so on. And we've got a certain distance with that, but it's a thing where there are many kind of mathematical physics directions to go with that. And I think the thing that, what one needs to understand is things like, okay, we understand the curvature tensor in any integer number of dimensions, but what is a curvature tensor like in 3.2 dimensions? There is basically no mathematics that's been figured out for that, and we're trying to build that. And we need to build that because in our models, dimension is a dynamical variable. So the fact that our universe is roughly three-dimensional is something that has to emerge from the model. And in fact, we fully expect there to be dimension fluctuations left over from the early universe, one of the interesting physics questions there is, how would you detect a dimension fluctuation? How would you detect that some part of space is 3.01 dimensional? My guess is that there will be some version of gravitational lensing that will happen as light propagates through a region of fractional dimensional space, but we don't know how that works. We'd really like to know how that works. Another thing we'd really like to know is, what are the experimental implications of these models? How do we make essentially a space-time microscope that can see down to the scale of the discreteness of space? We kind of suspect that the discreteness scale of space is around 10 to the minus 100 meters, much smaller than the Planck length, very tiny. You know, people with molecules at the beginning of the 20th century were lucky. Molecules were big enough that you could see Brownian motion through a microscope. We're not sure we're going to be lucky enough to be able to see any effect that reveals the discreteness of space using any kind of technique that exists now rather than centuries from now. But that's a challenge, is can one figure out some effect with black holes or jets from black holes or critical black holes or photons in orbit around black holes or something like that? Can one find something? Can one find a hack, basically, that allows one, since this is a hackathon, we're talking about hacks, we're talking about a hack to the universe hack. Can we find a hack that sees down to the discreteness scale of space? By the way, just in terms of hacks, one thing perhaps worth mentioning is, the ultimate hack might be make something that goes faster than light. And so it turns out in our models, you can kind of really analyze how going faster than light might work, because it turns out that the structure of space, because the structure of space is dynamic, it's kind of like if you want to go across it, if you're in a room and it's full of gas molecules and they're bouncing around randomly, and you want to go, you have a smell or something that starts on one side of the room, it's going to go to the other side of the room. It doesn't, although the individual gas molecules are traveling at the speed of sound, roughly, the smell travels very slowly because it goes by diffusion, because it's waiting for, each random collision of molecules to transport it. If you could pick the exact right molecules to hitch a ride on, you could go from one side of the room to the other at the speed of sound. And it's the same kind of thing in space-time. If you could pick exactly the right rewritings to decide to ride on, you could go across space faster than the speed of light. The problem is, it wouldn't be you doing that, because at the scale that it's possible to sort of untangle what's happening, there's sort of a huge amount of computation needed to untangle it, but also something like us, an observer like us, just won't fit at that scale to be sort of an us-like thing. So unfortunately, even in our models of physics, although in principle you can make a hack that goes faster than the speed of light, in practice you can't stuff a consciousness like us through it. All right, there's much more that I can say. There's many things that have been done, figured out, many things that haven't been figured out in our physics project, but I think I should stop and we should see if there are questions or comments or things we can talk about.
Wonderful. Any questions for Steve?
Thanks for the talk. That was really cool. So I was wondering, does the physics establishment agree with you?
I was sharing, wasn't I? I wasn't just talking.
Oh, no, you weren't. Yeah,
screen.
no, the visuals are amazing, honestly.
Sorry. Was the you did see the screen, right?
Oh, we did, yeah.
The visuals were amazing.
Okay, good. I was just checking because my Zoom seemed to say I hadn't been sharing. Yes, please go ahead.
Yeah, so I was wondering, does the physics establishment agree with you? And if they don't, what's their main critique and how valid is it?
When I first started, when I had a chapter in my book, New Kind of Science, that came out in 2002, my friends in physics, some backstory. When I was a kid, I was a physicist. And, I did a bunch of work when I was a late teenager, actually, which has survived very well back from the 1970s. So I was kind of a top operative in traditional particle physics and cosmology. Actually, I was one of the early people who kind of tried to merge particle physics and cosmology. So then I haven't been a physicist for a living for a very long time. But, it was kind of a strange dynamic because in 2002, I brought out this book, New Kind of Science, that's mostly about thinking about computation as a foundation for making models of things. But I had one half of one chapter about fundamental physics. And my friends in physics at that time were like, oh my gosh, this can't be right. this is so different from our existing paradigm, it's totally shocking, we're horrified. Okay, so that was one of the consequences of that was I figured after that, it's like the main market for theories of fundamental physics is physicists, they don't really want this. I've got plenty of things I can build, like Wolfram Alpha and so on, that which people really do want, so I'm going to do that. So then 20 years went by, and nearly 20 years, and I made sort of a little bit of a technical breakthrough, and then a couple of young physicists got really excited about this and said, you've got to do this. And so I said, I'll do it if you work with me on it. And so in 2019, we started really seriously on this physics project and released kind of it in 2020. Okay, the reaction of the physics community to version 2 was completely different than version 1. Basically, the reaction to version 2 was, oh, this is interesting. And then the realization that there were all these directions in mathematical physics, whether it's loop quantum gravity, spin networks, causal set theory, or even string theory, although a little bit less energetically there, where people said, oh, the thing we've been studying for a long time is actually a limit of the thing that you've been looking at. And in fact, the thing you've been looking at informs the things that we've been looking at and the things we've figured out are relevant to your way of doing things. So I would say that basically, I don't think anybody has a big, oh my gosh, this can't possibly be right. Back 20 years ago, people were like, oh, but we know the universe is not computational. We know the universe is governed by partial differential equations and quantum field theory. That disappeared in the intervening 20 years. Maybe as a result of the failure of string theory, maybe as a result of kind of increasing understanding through sort of quantum information stuff of the relevance of computation to physics kinds of things. Maybe just because 20 years went by, and well, another thing that happened is sort of as, one of the things from my New Kind of Science book and related efforts, the idea that computational models were a good way to make models of things really became pretty mainstream, and I think that probably has helped. But I would say now, the dynamic, I would say it's a pity more hasn't been done making bridges to existing areas. I mean, people know that basically there are, as I say, that there are existing directions in mathematical physics which are limits of what we've done. There are different communities, like the causal set theory community is pretty into this. The higher category theory community seems to be pretty into this, at least the corners of it that relate to things like categorical quantum mechanics and so on. But I mean, we are, one of the things about history of science is that in retrospect, people always say, oh, and there was this new theory, and immediately everybody realized it was the right theory and jumped on it. That's never how it actually happens. The actual way it happens is grindingly slow and takes decades and so on. But I think we're actually things are going faster than I might have expected. And so far as I know, I don't know of any, oh my God, this couldn't possibly be right. 20 years ago, it was like, we know the universe isn't computational, but that's gone away by this point.
Fantastic. Second and final question. The use of artificial intelligence to search through this space of notable universes is a project of interest. What do you see as the position of AI in the problems that you're working on when it comes to discovering universes that reliably surface the totality of the laws of physics?
Yeah, sorry, if you could just give me a couple of minutes. I told you I was not in my natural habitat here. Okay, so, one of the things that I seem to spend my life doing is looking at big arrays of little pictures and trying to figure out interesting things from them. So obviously I have tried to use AI for years to do that. The problem is that what I'm really looking for is the unexpected. And that's actually not, I can do anomaly detection. I've done that a zillion times. Maybe there are things you can get from that. I'll show you an example. Just a very, let's see if I can pull this up. Now, what is this shown? Is that shown?
It's being shared.
Yeah. It is shown. Okay,
yeah.
Sorry, it's just really confusing here. Let me see. Let's see. I think I have some. Yeah, here, for example, I looked at, these are different kinds of possible results of hypergraph rewriting, and, that's a feature space plot of that. And you can see that, this is just default feature space plot in Wolfram language. It might not even, this is from 5 years ago, so it might have even sharpened itself up since then. But you can kind of see there are the worm-like critters, there are the kind of cycle-like critters, and it's sort of useful to be able to see that. I mean, one feature space plot, I think this is one based on visual appearance, this is one based on adjacency matrices. These are things where, yes, you can get, this is a way of helping, sort of helping the human to sort of do better what a human might otherwise do. it has not been spectacular for me. Actually, in that particular case, I really did use that. That was a few years ago. I really did use that in finding sort of anomalous things. That was quite useful. Now, today, the other thing really interesting is literature mining. So, there's the question of, it's like there are these effects I want to find about sort of dimension fluctuations. Even knowing something that I wanted to know a few years ago, what are all physics formulas in d dimensions, rather than 4 dimensions or 3 dimensions or whatever? What are the formulas in d dimensions? So you can try and look in the literature, and it's actually quite hard to find that. I don't know, I haven't tried. I should try, I should just try looking up, give me all physics formulas in arbitrary dimensions, because that'd be useful for trying to see what are effects where one can see dimension fluctuations. But, it could very well be that somewhere in the literature of physics, in places that are where there's no keyword you can search for, but where there's sort of a rhythm of what's being said that kind of resonates with things like dimension fluctuations. So that's another thing to look for, I think, would be really, really cool to find.
Fantastic. Thank you, Stephen.
I think off I have to go to a totally different conference. So see you guys, good luck, hack well, and figure out some really interesting things. We have James and Dugan from our team are there, so I hope they're there. Are they there?
Yeah, they'll be here. James had
James
to step out, but he will be here.
We'll be there in 5 minutes.
Yeah.
Oh, okay, fine. All right, okay. They're virtually. All right. Have a good time. Hack well. See you another time. Bye.
Bye, Stephen. Okay. So.
Continuous space dimension is discrete, but in discrete space dimension is continuous.
The beauty. So yeah, I guess for context, the original name of AGI House is Neogenesis, which is a name that is about this sort of maximally ambitious scientific and technological frame that with sufficient progress, we will be able to recreate the universe using science and technology. And so I feel like we are as close as we have ever been to the realization of that with this talk at this event. So lots of love for that perspective. But okay, so there are so many perspectives on physics, much more practical than that. So we are about to have a number of fantastic speakers for you. Let me grab the ordering real quick. So up and coming in person, first we'll hear from Micron Ventures, Surya. Second, we'll hear from Richa Sharma, quantum physicist. Next will be Amir, one of the creators of AlphaProof and alpha geometry. And finally, Fred, the co-founder and the CEO of Multiply Labs. And so, a number of really fantastic and fascinating perspectives. First and foremost, though, let's hear from Micron and Surya. He's the co-founder of Multiscale Technologies, and they have put together what I would say is truly phenomenal technology. And Micron is a sponsor that makes this event exist. So let's hear a huge round of applause. Thank you.
Yep. All right, good morning. Everybody doing well? Name is Tian Yu. I go by TY. I'm from Micron Ventures. I just want to say upfront, I love Silicon Valley. Right? Only in Silicon Valley on a Saturday morning, you wake up to a talk talking about the origin of the universe, and now I have to follow that. So challenging. So very quickly about us, Micron Ventures. So we're the VC arm of Micron, the semiconductor company. So on my way over, I thought about like, how do I introduce ourselves? What do we invest in? If you think about our investment, we're into the picks and shovels of the AI gold rush, right? So from semiconductor to compute to infrastructure software to enterprise AI, those are the things that we invest in. Now, I want to thank Xenia and Jeremy for inviting us to this, because for us to do our jobs properly, we want to capture the early signals of what's happening in the market, right? Now, early signals are what the cool people are working on, thinking about, working on, right? And you guys are the cool people, right? So if you want, this is the QR code to my LinkedIn, right? Scan it, catch me for a chat about the company you're building, the things you're thinking about, or just random topics, right? So that's that. Now, I want to introduce to you Surya. So Surya is a tenured professor at Georgia Tech, and he is the co-founder. So this is my dancing moment. So he's a co-founder of Multiscale. Now, Multiscale is a portfolio company of ours. So they are in the space of using really deep AI techniques to solve for optimization problems in design, manufacturing, enterprise processes, right? Now, we had a great chat a few days ago about what Multiscale does. I want to give you a simple analogy, right? So, and this is the analogy from Surya. So he said it took Edison 10,000 tries to get to a light bulb, right? Multiscale is in that business to do that with 200 tries, but yet build a better light bulb, right? So that's my little pitch for Multiscale. So without further ado, Surya from Multiscale.
The room is small, I guess. You can all hear me?
Oh, okay.
Yeah, so let me just switch this to yeah, so I'm an engineering professor, so I really cannot follow the previous talk in any sense of the importance of universe and how we are here and why we are here and all that stuff. I deal in very practical things. The only thing I know is Micron invested in us, and so we need to make our customers money. Bottom line, on a day-to-day basis. Any day we don't make enough money for our customers, they'll kick us out. So, so is this working?
Yeah.
It is working, okay. So the kind of problems we are solving for our customers, I mean, again, this is the engineering definition of physics. So it's interesting sitting there and thinking of, oh my God, there's this entire physics definition that I'm not even thinking of. An engineering definition of physics is we are interested in two types of problems at a high scale. But bottom line, mathematics, from a mathematic viewpoint, they're all either optimization problems or inverse problems. And oftentimes, it really comes down to the product from our customer, and they're trying to maximize the performance of the product while minimizing the cost and also the speed of innovation, because there's also a concern that the competitors are going to get ahead of them to the market, and somehow you need to get there faster. So all of this translate to optimization problems. And I argue that pretty much 100% of the activity, almost 100% of the activity in engineering technologies comes down to optimization problems. And here are some examples of some of the current customer problems. And again, the reason I'm here is I'm hoping that some of you are interested in this. We have a fairly new set of customers in this area, so we are trying to pull together a team here. So we are hiring. So if any of these problem sets are of interest to you, talk to us. We are here. Okay, that's one of the main reasons I'm here. So, okay, so the kind of problems of interest is in the semiconductor space, the latest thing is, you must have heard about CHIPS Act, the reshoring problem, right? Now, at one point, US was the dominant producer of chips. This was way back, though. And then we suddenly became almost zero, nothing. And now the idea is that we need to reshore the technology back onto the US side. And of course, in this new form, it's not going to look like what left us. It's going to take a completely new form. And exactly how is that going to look like, and what is that going to look like? So there are problems of this kind that we are solving for our customers. Most of them deal with essentially maximizing the performance, the wafer yield, for example, the number of good dies and good chips that you can produce. And also there is this co-optimization problem where if you look at the semiconductor manufacturing today, it's almost about 1,000 steps. Each step has to do with either putting a layer of a metal layer or drilling a hole and then putting another layer or cleaning it up, things like that. So it's usually that kind of process, but it's actually amazing the number of steps they do, and the precision with which they lay down those layers is absolutely phenomenal. And again, 2 or 3 years back when I got into this, I come from mechanical and material science, so I actually didn't know any of this stuff. And then when I saw what they do, I said, boy, this is the most high-tech manufacturing industry in the entire world. There's nothing that, as far as I know, nothing that beats that. And they have very complicated or very intense optimization problems. Imagine that there are 1,000 steps, and each step at least has about 20 knobs you can change. So that means you're trying to optimize the process over 20,000 dimensions. That's humanly impossible using most of the techniques that are available today, or the classic techniques that we teach in undergraduate classes or graduate classes. So those are the kind of problems. I'll show you what we're doing after I go through this. And of course, EVs, the biggest issues are, everybody knows about battery, so I'm not going to say much about that. The bigger issues that we're looking at for one of our EV customers is crash resistance. So here the problem really is, how do you maximize crash resistance while minimizing the amount of material? So they want the weight to be lower, so you need to reduce the weight. But of course, usually when you reduce the weight, you're also not making them structurally strong. So you have to find a balance between the two, right? And those are not simple problems, very complicated problems. And of course, the space I come from a training point of view, is really metal production. So these are where you make aluminum, steel, and things like that. Oh, 2 minutes, okay. So let me jump. And I think I'm doing it like my usual lectures, which take an hour. So I'll speed up. So we solve problems across the entire technology stack, all the way from R&D to plant manufacturing to packaging and testing. These are the core areas that we build on. Essentially, in a nutshell, the problem that we really deal with is, in all of our problems, the amount of data is very little. So one row of data or one data point is very high dimensional, often of the order of 100,000 dimensions. The number of columns are 100,000 dimensions or bigger. Every row costs anywhere between $10,000 to $1 million, depending on how you generate that. So data is not very easy to get. And so the problem we are actually solving is not what do you do after you collect a lot of data. The problem we are solving is actually telling them where to get the data, where to invest their next effort, because that becomes the bigger issue. Because by the time you have a lot of data, you actually have already solved the problem in many ways. Okay, so to do that, it is always a question of what is my next best step? Should I do another physics simulation? Should I do another experiment? Which one? Should I do this experiment or do I do that one? Because everything costs time and money. Every time you make a decision, you're kind of spending millions of dollars and at least 6 to 9 months. So there is a huge cost to any decision you make. So without much more detail, and since I'm running out of time, the core model, because of the data scarcity, the approach we take is very Bayesian. So everything here is Bayesian. And essentially we quantify and propagate uncertainty through various terms. But we take data from physics-based simulations, like DFT calculations to finite element to even cellular automata and things like that. There are actual physical experiments our customers run. And then we actually connect the calibrate the experiments with the physical models and using Bayesian approaches. And so there are a lot of reasons as to why we do this, but this is our generic statement, a generic framework. We argue that this can be applied to any complex physical system without any exclusion or limits. So we pretty much deal almost all the problems fall into this space, into this problem space. I'm going to skip because I don't have enough time. I'm sorry that I'm running out of time. So the problems, the organizers asked me to outline a problem space, just in case you're interested in this. I don't know how interested you are, but I'll say this is what, because most of our data sets are proprietary, so it's very hard to give you access to them. But this space there are plenty of data sets out there. And in this space, what you're really trying to understand is the arrangement of atoms. So species of any atomic species in the periodic table is a possibility. And how do you arrange this such a way that you get a certain combination of properties you're interested in, right? So just to give you a basic idea, people have done this without paying enough attention to structure. They actually do it just based on composition. And that's not very useful because the example we always give is carbon. If I don't tell you anything about structure, it could be graphite or it could be diamond. And graphite is the softest known material to man, and diamond is the hardest one. So there is right. So you have to actually pay attention to the structure. And the structure here is a very periodic and structured, but a lot of polymers don't even have periodic structures. So this can get very, very, very complicated and very high dimensional. And that's where the challenge is. But most of the interesting problem combinations happen only in complicated structures. That's where the challenge is, and that's not a trivial task. So with that, I'm going to stop.
So to be clear, these 3 data sources are all materials databases from which you could create a generative design space for quality materials and attempt to optimize for these outcomes of interest.
So the hard part is the generative part, is that these databases start with structure and then they tell you what are the properties that are estimated using density functional theories and things like that. But now coming back to saying what are the feasible structures, that's not a trivial task.
What is the state-of-the-art open model which could be, say, DPO'd or RLHF'd to optimize for particular properties in the generation of a novel structure?
Yeah. So there are two answers to that. One is the one that I alluded to, which is simply based on composition. So they're simplifying the structures to such a low level that I don't find it very useful. But there are people who do that, right? Again, you can always say some answer is better than no answer, and that's okay. And then there are people who do this with the structure information, but then they limit to a particular class of structures. But there's no such thing that covers all possible structures. That would be the value. Sorry.
I have one question. If that's
Sure.
okay. What's your take on synthetic data, or what's the bottleneck for synthetic data for this space, the material science space, given its data pool?
Yeah. So two bottlenecks actually. One is the DFT calculations themselves are pretty hard because once you get the charge density field, that's the easy part, right? Then estimating these properties from the charge density fields are not that trivial. And they have limitations in the sense that they are ideal for 0 degrees Kelvin and things like that. So how do you actually use it something for a real application, especially when you get to applications more in the structural part? I mean, so we normally break this down to structural properties and functional properties. Some of the functional properties are much easier to predict. And the structural properties are incredibly hard to predict. If I want to predict the strength of a material, you simply cannot do it at a DFT level. That's very, very difficult, right? And the other bottleneck is ground truth, experimental data sets. And they're also not very easy because it's easy to measure at a bulk scale, but it's not easy to measure at a single, at a single crystal, pure single crystal level. Those are the issues.
How is FEA generally done for MEMS?
Say it again, sorry.
Last question, by the way.
How is FEA generally done for MEMS?
Finite finite element analysis for MEMS.
Yeah. Is it generally done at that scale?
Oh, so most FEA is at a higher length scale. So we are not talking at, I don't know. I mean, I'm happy to talk to you if you have a chance. Usually at this level, it is DFT, MD, and so on and so forth. At a higher level, you do FEA, and then you have to account for crystal structures, polycrystals, and things like that. So we do a lot of that in some of the other work we do. Okay.
Fascinating. Up next, we have Richa Sharma, PhD in quantum physics and wonderful co-organizer of our event. Let's hear it for Richa.
Hi guys, I'm Richa, and so yeah. Let me know. I really suck at making presentations, but I'll try my best to give you an overview of what's going on in the intersectional world of machine learning and quantum computing. Or broadly, like what is like going on to accelerate science and how we can like come in and just like reduce the bottlenecks. So AI X physics, like it's pretty self-explanatory. We are trying to accelerate science. So when we look at physics, physics is one of the most powerful tools created by man to understand the machine that is the universe. As human beings, we just have imagination and we want to explore the worlds that exist in this enormous space. When we look at the problems like black hole physics, or when we look at strong forces and holding elementary particles together. So it's just, you see that the physics controls, if you coarse grain it, you can just go to the smallest things that ever exist and to the largest things and the largest scales that ever exist. If these strong forces are not holding the protons together, you will see these things completely scattered across the space. One of my favorite examples came from when I was just getting started in the 10th grade and trying to figure out what I wanted to do with my life, was from Feynman's lectures of physics, when he was explaining if, say, Wendy or Robert are standing at one arm apart, and Wendy has 1% of electrons more than the protons in her body composition, would Wendy be able to lift Robert? And the answer is, yeah, but what would be the actual magnitude of the force? What would be the exact thing that this magnitude of force would be able to lift? Would it be Empire State Building? But the answer is, Wendy would be able to lift entire Earth. So the way the world is set up, it just works. And we are here to discover more and more that why that is. So we have broken this machinery, and we have actually harnessed the nuclear powers with atomic bombs, fission, fusion, and it has basically left humanity in completely awestruck. And we have gone with one of the best theories ever developed by man, Standard Model, in the terms of like experimental quadrillions of collisions, and it has proven true over and over again. But we haven't really seen these benefits trickle down in the same way that other inventions in the early 20th century has, and the prosperity that has like trickled down in the civilization. But why that is, why we are like basically stagnant in the terms of quantum computing, or even particle physics to actually go down the same path as like artificial intelligence and other models like AlphaFold has. So when we think in terms of, I just want to touch on like how I personally think that AI could be most helpful. And AI, we can think it of as a computational microscope. What that means is that instead of actually collecting the data, or we can actually train without the data. In certain many-body physics problems, we can density estimate through generative data. And this is like one of these examples where the underlying probability densities can be computed. So things like that. It just makes you really think and that what exactly is this scientific, like these bottlenecks we can remove. One of my favorite examples that have come out is this cross-test foundational model for particle physics. This is OmniJet Alpha, and autoregressively they're able to generate these jet tokenization in the representational space, and it is pretty impressive with the amount of possibilities that exist, and the amount of precision that was able to be achieved in such like short point of time. So going back a little bit on like one of the problems I was working with, which is spatially dependent disorders in quantum walks. And quantum walks are pretty important in quantum computing in general. It's also one of the reasons why quantum computing is advantageous over classical counterpart. So when you see this assimilation over here, it basically means that quantum computing it's not diffusive, it's ballistic. It hits the next node really fast, instead of the random walk, which is a diffusive walk. But if we keep on increasing disorders spatially and hierarchically, if you see that it actually kind of becomes slower and slower if you increase these parameters, diffusives. So it took me about like a month to generate these simulations, and I was like going back and forth from C++ and Python. And so I just want to say like how more and more we can go and innovate on these kinds of things. So I'm going to wrap up. So machine learning for experiments, obviously Hamiltonian learning. So how we can actually reconstruct the map of the underlying Hamiltonian and many-body physics. And so if you also, there is not an aspect of quantum computing and quantum physics that machine learning cannot be applied in, just by the pure nature of the mathematical and computational intersection that exists. But this is also another interesting example of RL agent framework, which you can find optimal relaxations. And so, I'm just going to wrap up. And a lot of this talk was obviously taken and inspired from Peter Wittig's, one of the most fantastic books I've ever read. And so this is modern applications in machine learning, really recommended. And so I'm also a startup founder, and I am building physics foundation models for spatial intelligence. It's just like world models, but it would be physically aware and multi-domain physics. So I think this ends my time. Come on.
Okay, so we had hoped to have Amaya here for an AlphaProof presentation last week at the AI Mathematics Hackathon, but in a lot of contexts proved to me as important in the context of physics, and I also hope that the same techniques that underlie the kind of proof search that is done here can be applied in more applied physics contexts for the discovery of high quality models in general, And it is fantastic to hear about the automation of this essential aspect of mathematical research. So let's hear it for a man.
All right, yeah, thanks to Jeremy and Cinia and the rest of the AGI house for inviting me here. It's a little bit last minute, but hopefully I don't go into the 1 hour lecture mode here. It's really hard to give like a 5-minute talk, but I'll try my best. Okay, yeah, so I'll get into it quickly since we're low on time. So I'll be talking about AI and the intersection with physics, but also really math, which is kind of the core of what I'm talking about. Okay, so I think one of the big questions that people have been concerned about, with the advent of AI and the proliferation of it, is whether AI models can actually reason, right? Do they actually exhibit reasoning capabilities? And I think mathematics is one of these nice areas where you have problems that have a logical series of steps. There's some kind of mathematical language that is very precise. So people have looked at whether AI models can reason with concrete mathematical problems. And people have chased various benchmarks for math. So there's this famous Hendrix math benchmark that maybe a lot of you know about already, which consists of contest problems. They're mainly simple kind of questions. I'm not sure actually how easy it is to see the slide. It's a little bit blurry, right? Yeah. Okay, so, but anyway, you can see a couple of questions there that are kind of samples. And mostly they have numerical answers, so there's kind of one final answer you're trying to get at. Yeah, maybe it's a little bit better. Okay, and I think recently we've gotten to a pretty good level with the math benchmark. We have 80-90% accuracy. So the question now is whether we can solve more complicated problems, things like proofs, things that don't have a single numerical answer. So one of the projects that I was involved in at Google, and I was at Google until very recently, so I'm taking a break, but this was released about 3 months ago. This was the AlphaProof and AlphaGeometry 2 models. So they were kind of milestones in solving more complex mathematical problems. So we looked at problems in the International Math Olympiad that occurred this summer. So there, for those of you who are not familiar, those are more complex proof-based questions. So there's kind of 6 questions that contestants answer in 9 hours. And our models were actually able to solve 4 of the 6 questions completely. Combinatorics was sort of the weak area where it was not able to make progress. So we were able to actually get a silver medal with this model. And actually we were only 1 point away from gold. So maybe if we had gotten a partial credit on the remaining combinatorics questions, we might have gotten a gold. But anyway, this was far beyond my expectations when I first started working on this. So I won't have time to get into too many details, but I'll try to describe some high-level aspects here, right? So, and there are kind of 2 models, AlphaProof and AlphaGeometry 2. AlphaGeometry side, that's geometry specific, and AlphaProof was used for pretty much everything else. I myself worked mainly on the AlphaProof side, so I'll talk more about that. So the idea there is to kind of combine LLMs with this AlphaZero based system. So some of you may know, but AlphaZero is this technology that was at Google DeepMind that was used to solve things like Go and chess. Again, domains where there's clear set of rules and clear set of steps, and it does some kind of traditional tree search kind of exploration. So essentially, the main network is kind of this AlphaZero based part, except instead of having a game like Go or chess, we have these mathematical statements and your steps. Basically there's this language called Lean, which allows you to actually formalize all mathematical statements, right? So you can, it's gained some popularity over the last few years. People like Terry Tao and others are trying to formalize a lot of mathematics in Lean. So you can basically describe any statement in mathematics in Lean, and there's a series of steps, kind of what tactic to use next, and sort of what step to undertake in the proof. So you can do an AlphaZero type of search in this Lean space. And now, one of the issues that came about is, okay, to train this network, you need some set of problems, right? It's not like Go or chess where you can just kind of start playing against yourself. And if you kind of scour the internet for data, there's a lot of math problems, there's a lot of math content, but there's very little that is in this formal language called Lean. Okay, so you'll try to find all the Lean data you can, and you'll pretty much run into a wall fairly quickly. So one of the innovations we did was we built this formalizer network, which kind of takes in natural language statements of math problems and math content, and it formalizes it into this Lean space, right? So essentially we fine-tuned some version of a Gemini model for that. Okay, and this allowed us to get like in the hundreds of millions of problems that we could actually train on. Okay, so just to give you a sense of how this works, so this is the hardest question on the IMO. Very small percentage of contestants solved it. It's this kind of complicated, functional equation kind of problem. And, our system basically outputs something like this, right? This is something in Lean. I guess you can't really see it that well, but it's kind of like a programming language for mathematics, I think, is how to think about it. Okay, so I'll make some connection to physics here, but I think the main thing I want you to take away from this talk is probably on this slide and the next one. So essentially, AlphaProof and AlphaGeometry 2 are neurosymbolic approaches. So what's going on is we're combining symbolic systems, things like formal logic, with neural networks, right? And I described, that diagram in the previous slide. There are other approaches people are taking that are neural network only, things, I think other companies like OpenAI, they have this one family of models where they're primarily solving things in the natural language space. So there's this big question of kind of, what's the right approach, which will win out, right? And, you can take this kind of historical approach of, in the 1960s and 70s, we really saw things like the perceptron that was the underpinnings of kind of modern neural nets. We ran into some walls there because, we didn't have the resources or NVIDIA wasn't around, I guess, basically. Then we moved to these kind of symbolic knowledge-based systems and ran into a wall there. Then there was this kind of AI winter, as they call it. But really, I would say it's more of a focus shift because I think people moved to solving things like search and recommender systems, which I think we made a lot of progress on. And now in the last 10 years, obviously, neural nets have gained a resurgence, but it's kind of like neural nets plus what I call the kitchen sink, where we use all these other tools, right? So use symbolic approaches, use tool use, whatever we can. So I would argue, I think it's important to kind of keep an open mind, and maybe it's true that you can just do reasoning in the natural language space, and you don't need any of this symbolic reasoning. But I would argue that even if this is true in the long run, the kind of quickest way to make progress in a shorter term might actually be through these neurosymbolic approaches where you're combining the kind of formal language, formal verification kind of methods and neural nets. I think this is especially true for structured domains where you have a lot of kind of structure to the problem, a series of rules or steps that have to occur, because I think there's kind of this increasing belief that LLMs kind of inherently have hallucinations. So there are some domains where you can't tolerate that at all. There's a large risk to having hallucinations, or domains where that additional structure really helps. So I think we saw in Stephen's talk at the beginning, he was talking about mathematical physics and a lot of things that are based on kind of concrete mathematical theories or equations, right? So I think these are particular domains where this kind of approach is useful in thinking about things. Yeah, so to give you just a sampling of this is kind of my last slide. There are these areas of physics where I think if you're trying to target new scientific discoveries, and I like the fact that Stephen mentioned this at the beginning, right, where what they're trying to figure out is, and I think Jeremy, you asked a really nice question at the end there, how can we actually discover new things, right? I would argue that pursuing this kind of neurosymbolic approach is one prong of how we can maybe do that. There are some works that are looking at this, for instance, formalizing chemical physics to enable scientific discoveries there, and they're actually using Lean, so I was quite happy to see this. Things like quantum programs, quantum circuits, how to kind of verify what they're doing as quantum computing takes off. I think this is kind of related to software engineering as well, where you want programs that are kind of doing what you want them to do, and how can you verify things like this. There's also kind of an interesting area maybe going the other way, which is can we build neurosymbolic architectures that are physics inspired, right? So in Gen AI, we've seen things like diffusion models, which are inspired by thermodynamics, and can we see more of these kind of architectures? So I think this is kind of a budding area. I think we've really only scratched the surface up until now, and hopefully I can inspire some of you to think about some questions in this area. Okay, thanks a lot, and I have some of my social media accounts up here, so feel free to scan the QR code and reach out. And to the hackers, hack on, and hope you enjoy the rest of the day.
So a question, I guess,
Yeah.
as an open tool for us to build with today, what would you recommend? Do you think the Quen series of models, mathematical skills, as high as it might be hyped on Twitter, we should use Quen 2? Are there AlphaProof, alpha geometry-esque systems that are open source that you think might be interesting for an event like this? And I guess on the applied math side, is there anything that you think has a similar neurosymbolic approach to mathematical modeling, for example, but could be applied in a practical way? Perhaps even to problems in physics.
Yeah, I mean, so I think that, I don't know too much about Quen, so,
Sure.
but I think, in terms of kind of a tool, so I think there are a couple things that would be pretty helpful, like in this area. One is if we can get more mathematics people to use Lean and try to formalize a lot of their proofs and theorems into Lean, and I think there's some of that happening now. I think Terry Tao and others have given it some exposure, Tim Gowers. So that's, I think, one part of it. My hope is also that something like AlphaProof we can actually release to mathematicians so that they can use this as a tool. I think there's some discussion about that happening. I don't know if there's kind of consensus yet, but that's kind of my hope, where this is really a tool. For all people to use.
I also hope when people don't release things that they have some secret plan by which it will be used for lots of important tasks. Hopefully it's a sign that AlphaProof matters.
Yeah, I mean, I think there are a lot of people who share my view, I would say. So
to release it, basically.
Yeah, so
One more question.
we'll see what happens, yeah.
You mentioned combinatorics problems weren't as good as others. Do you have any speculative hypotheses as to why and what can be done?
Yeah, this is actually one of my kind of questions that I've been very interested in, trying to understand why that is. I don't have a concrete answer, but I have a couple of guesses. I think, first of all, I think formalizing a lot of combinatorics questions can be trickier than, say, algebra questions or number theory questions, or whatever else shows up on the IMO. Just to give you some intuition for why, one of the questions on the IMO that our model was not able to solve, which also actually ended up being quite hard and very few contestants solved. It was one of these questions where, just to give you a rough idea, it's like you have some kind of chessboard or rectangular board, and you start at the top and you want to get to the bottom of the board, and you have to make some series of moves, and there's these landmines, throughout the board according to some set of rules, and then every time you hit a landmine, you have to start over. And then the question is kind of, what's the best strategy, and what's the minimum number of tries you need to successfully complete this task? So that kind of thing, just to formalize that in Lean is actually quite hard. In fact, some of us did it by hand, and it took 3 hours just to describe what the problem is, right? So I think this kind of thing is much harder in combinatorics. I am not sure that's the only reason. I think there's also something to the set of tools that are used to solve combinatorics questions tend to be a bit more ad hoc. I don't know how to precisely say this, but that's kind of the intuition. Whereas if you look at sort of the other types of questions on the IMO, like geometry, there's kind of more of a kind of set defined toolkit, I would say, to solving those kind of things. So that would be my guess, but yeah. Yeah, I'm happy to answer more questions later. You can come find me. Yeah.
Thanks so much, Fred. Appreciate it. Sorry, up next is Fred, excuse me, the co-founder and CEO of Multiscale Labs, and they are interested in working with you on problems in robotics. Also, a beloved sponsor of the event. Let's hear it for Fred Arietti.
Thank you.
Okay, so let's see if it works. I have a lot of videos, so. Oh, no audio. Okay. Great. Okay, great. It's great to be here. Thank you for having me. My name is Fred. I'm co-founder and CEO of Multiscale Labs, and we develop robotic systems with a very, I would say, physical application, which is biomanufacturing. So we're kind of at the intersection between inorganic technology, so robotics, but also organic technology. And so I'm going to in particular, manufacturing genetically engineered, basically, drugs for patients. And I'm gonna quickly introduce, what we do and why AI, and in particular the application of AI technologies to the real world is so important. And right now, I would say a giant bottleneck in this space and the pharma space in general. So first of all, what do our robots do? And I think the best way is to show you how drugs are made today in this is kind of a video from a large pharmaceutical company, no relationship to us, but everybody does it this way.
Manufacturing facility at its global R&D center in Boston, Massachusetts.
We don't need that. So it's basically artisanal right now how cell therapies are made. Yeah, so imagine, tubes, everything is connected by hand, right? It's basically, I guess, where driving was before self-driving, right? And where I don't even know if semiconductors were ever at that point. They were not called, I guess, microchips, right? Nobody can even try to make them by hand, but in bio, that's the status. So how do we go from here to basically an automated, I would say, self-driving, large-scale manufacturing of essentially genetically engineered drugs? So I will show you what we are doing and why I think the application of advanced technologies like imitation learning is a big part of the answer here. So first of all, so I think you saw very clearly the problems. I'm not going to dig too deeply here, but there is at least like 250,000 people that need cell and gene therapies today in the US. And maybe less than 10,000 get them every year. Every therapy is a couple of $1 million. So like this is a big, valuable problem. And so I would say the first step to apply, I think, AI in the physical world is you need to have very reliable, very commoditized hardware that can scale. So a very good model throughout this talk, I think, will be what Tesla is doing, right? You get a ton of cars on the road. Those cars need to be very well engineered, right? And they give you data, but also give your AI algorithms an outlet to basically implement and affect the world. If you don't have reliable and scalable hardware, then your algorithms are going to be confined to the computer world, right? So what is that in pharma? So we actually do not re-engineer bio instruments. We teach our robots to use existing instruments. So that's the equivalent of, I guess, Tesla using cameras. Cameras are cheap, they are abundant, right? And you can deploy a lot of them at scale. We kind of, do the same in the bio world. So basically, the process today, you start from the cells of the patient, from a bag, then you genetically engineer them, typically so that the cell can, for example, recognize cancer or recognize an autoimmune disease. Then you get these cells to grow until there's billion of them, and then you infuse them back in the patient. So effectively, the artificial system, the robotic system, is taking the cells of the patient and genetically engineering them so that they can then be put back into the patient, and that patient has a better immune system, effectively an augmented immune system, right? So that's basically the base, the hardware, right? Scalable hardware that's already proven that we know can be deployed at scale. But the problem is, and by the way, we work with the largest basically hardware manufacturers in the space so that they can provide us with these hardware at scale, right? And the system is very modular, it's very parallel. The best way to show it to you is just to show you a video of the robots. So these are our robotic systems. Again, we don't need the music. But yeah, so you see the robotic system effectively operating standard hardware, commoditized hardware, but with a level of efficiency and scale and parallelism that it would not be possible by hand, right? And this is the first part of the problem. To affect the physical world with AI, you need scalable hardware. But once you have scalable hardware, you also need scalable software. And that is the problem here. How do you automate the learning of, a bunch of very manual steps like this? By the way, I heard before an interesting, question about synthetic data. You can't really generate synthetic data for these sort of tasks because what these people are doing in the lab or in the manufacturing space is they're not just moving a bottle from place A to place B. They're also using their understanding of the cells to basically decide what to do. So what we need to learn and model is not just the physical task, but also the understanding of the scientist of the underlying biology. So that you can't really generate in an artificial, I think NVIDIA's been doing a lot of very cool work about synthetic robotic data, but those data have no understanding of the underlying biological world like a scientist would have. And so the idea for us is, okay, how can we basically generate a large scale of expert training data and then auto-train the robots so every new process can immediately essentially be implemented at scale on standardized hardware. And so the answer for us is, or a very promising answer is imitation learning. So I've got another video here. Wrong. Where we are, sorry. Here we are. Videos. So the idea is, okay, how can we basically learn from scientists, right? This data doesn't really exist, so the idea is, how can we put a ton of cameras onto a manufacturing floor and then self-extract basically trajectories and use these trajectories to self-label the tasks, of course, and use those trajectories to train their robots. And how can that be done at a very, very large scale for all possible permutation of a task? So this is a task, the one you saw before, where a scientist shakes a bottle containing cells. You need to shake it in a very different way according to how many cells are there, how well the cells are doing. And so the idea is that's the kind of expert demonstration that then you can use to auto-extract essentially training data, and then you use those essentially learned control policies really to inform the behavior of the robots. And so I would say, obviously this sort of stuff is quite computationally intensive, extracting trajectories from video data, but it's also, I would say, it's a safe bet today, provided that you have reliable and scalable hardware to basically assume that computation and data storage will basically be infinitely cheap and infinitely available. And so as far as basically we are concerned, having cheap and scalable hardware and using AI approaches that assume infinite computation and infinite storage is the way to actually solve these problems in the future, right? In a way that's not hand coding solutions for every task, because obviously I can have 10 engineers code this task, but that doesn't help us understand the other thousands of tasks that go on the manufacturing floor. So that's kind of like an overview of what we do. How much time do we have? Perfect, 1 minute. I would say actually I really enjoy, from this point of view, questions. And so I also have some extra material, but let's see if the questions go there, and I'm happy to show you additional videos as well.
I'm going to lead the witness. I think specialized robotics is the way to go, but I'm curious of your view of humanoids being more versatile and whatnot, or obviously you're building more specialized ones.
Honestly, it is true that these are more specialized than humanoids. Just a matter of designing, for example, giving this robotic arm legs, would cost a bunch of money and a bunch of time, and we don't really need it. It's fine to have a rail. However, this is a 6 degree of freedom robotic arm, which is comparable to a human robotic arm. And we are controlling it in force control, so it's a very similar way. So I would argue this is a quarter of a humanoid, the quarter that matters to us. So from my point of view, the problem is the same for humanoid robots, which is how can you, building the hardware must be done in a scalable manner. I think a lot of the humanoid robots I'm seeing right now are just not using commoditized hardware, or enough commoditized hardware. But even assuming they're plentiful and available, how do you auto-train those humanoids to do the millions of possible tasks? And so there must be a way to quickly extract that data from, demonstration, widely available demonstration, and then implement it on your scalable platform. And so right now, unfortunately, in robotics, there's really a scarcity, I would say, of data sets. Text won't make it, it's not enough. Even images won't make it. And even videos, can't directly be used to train a robot. At least you need to extract trajectories and maybe even an idea of interaction forces. So I think that step right now, extracting this rich data set from widely available data, like you saw before, the videos, that I think a huge bottleneck right now in robotics.
Is there some sort of, or would it be useful to have some sort of symbolic engine for biology? I know, just like we were talking about the presentation on neurosymbolic, models. I know OpenTrons have a lot of like subroutines where it like lists out a set of operations. Is that something that exists, or is that something people are looking into? Is that useful in this kind of problem?
Well, I mean, I would say definitely people are looking into that. Typically look into that from the point of view of drug discovery rather than drug manufacturing. I would say the big challenge, I think, with those symbolic approaches, it is that, if you're implementing a symbolic approach, are you limiting it by essentially defining the rules of the game? While, you could argue if you have even more data, right, and, and you train an even larger model, it might exceed the limits that you built in, you, the creator of symbolic language, built into your symbolic language. From our point of view, we're actually not trying to model the biology here. I just want the robots to behave exactly and reliably like the experts, because that would be enough to unlock basically plentiful genetic medicines for millions of people. So I don't think we need to understand the biology to get there, but we do need to have robots that are trainable at scale and with functionality that's comparable or equivalent to humans.
I see a strong emphasis on imitation learning, but wondering, like, even humans being put on a manufacturing floor are going through some specialized training before they can perform their task. How are we addressing that?
Well, imitation learning basically would scale, right? You only need a few experts, and if you can extract tasks at scale from those experts, that's great, right? So the bottleneck is not what an expert can do. The bottleneck is that you only have very few experts and millions of people that need those drugs. There's also another bottleneck here, which is regulatory, which means you're not free to optimize what the robots do. If the robots do something different than the people, then the FDA is going to have to reapprove the drug. So you actually want to learn as much as you can from people without changing it. So you have solid ground to go to the FDA and say, well, it's the same process as the humans, just at scale.
I think what I was wondering was, like, even humans, we don't expect to learn just by watching in certain specialized settings like this. So in that case, how is this imitation learning sufficient for the kind of training we want to achieve?
It's very simple. You need enough data, right? Because if you were expecting someone to train the robot by talking to the robot, then we would be inserting basically a bottleneck that the person needs to say the right things. And so the idea here is, what if we have just enough hours of video footage from a manufacturing floor? Everything that must be taught must be present basically in that data implicitly. And that's exactly what current AI methods are very good at doing, essentially extracting patterns from, plentiful data. The problem right now is that extracting robotic information from that data doesn't exist yet. Even before you start thinking about how do I get enough video, that's actually not the problem. At least the pharma companies we work with are desperate enough that we can get the video. It's just about a framework from auto-training the robot from the data.
Thank you.
Awesome. One last question.
Just a big question. Why is medication so hard to sell?
So hard to?
So
Artisanal.
Artisanal. Well, effectively, I think the best answer, but that's my personal, answer. The pharma industry has always been so focused on discovering drugs, because that's another, by the way, probably computational problem, completely separate from what we do, that the entire budget and energy of a pharma company is to prove that the drug works. After they prove that, basically they had no energy, no budget, no departments to actually engineer a reasonable manufacturing technology. And if you're just discovering simple chemicals like aspirin, right? After you discover it, it's super cheap to make it in a plentiful manner. But if what you discover is a genetically engineered cell, that's actually a very complicated lab experiment just to make it once. And so after you discover it, we see all these giant pharma companies that discover incredibly effective genetic medicines and can only make a few thousands a year, typically only for the US. So there is a huge manufacturing bottleneck. Okay, thank you very much.
Thank you so much.
Fantastic. So, before we jump into lightning talks, this is actually a fantastic opportunity for every hacker to describe their hackathon intention to everyone else. And so, what I'm about to show you is a spreadsheet that you all have access to, and it has a tab called Project Ideas. Sorry, let me jump in this. Sorry, for some reason.
I assume that's not the one we have access to.
Yeah. Okay. And so yeah, it's 1:52. So I guess I'm gonna give everybody 2 minutes to open up this spreadsheet and add your project idea. And that way, as lightning talks are going on, people can see what you and others intend to do. And so my request is that rather than starting talking, do open up this spreadsheet. I'll resend it out over the Particle. Add your project idea, and we'll get to watch it populate for the next 2 minutes with fantastic AI cross-physics projects. The Wi-Fi password is attention is all you need. Attention is all you need.
Lowercase or all caps?
All lowercase.
Jeremy.
Please, no talking until you signed up. So unless you're one of Thaddy, Manny, Brian, or Clovis, please, instead of talking, open up the spreadsheet and add your content. Thank you. 1 minute, 10 seconds remaining to get up.
Is there another way we can actually use spreadsheet?
I reblasted the Particle and I also added it to the Physics Hackathon Slack. But if you, yeah, I can text you.
Yeah.
40 seconds left. Okay, that's time. And with that, we turn the mic over to you, the hackers. So the opening lightning talks will be from Brian Yu, Ernst Young, Rick Goldstein, and James Wiles. So do please form a line going down this path next to the library in order of your talks. Is there anyone who'd like to give a lightning talk who did not sign up? Just raise your hand. This is a pitch of your project to the group. Okay. You do? Okay, please do join them in line after the fact.
Or I could just bring my laptop.
And with that, on intelligent fault detection and recovery for aerospace systems. Let's hear it for Brian Wu. Yeah, please hold the talk to 1.5 minutes. 1.5 minutes.
Okay, sure. Hey guys, my name is Brian. I'm a grad student at Stanford Engineering, and this is actually my first time at AGI House, so it's great to meet all of you, and I'm really looking forward to it. So, my research interest primarily focused at the intersection of AI, automation, robotics, and aerospace applications. And one of the things I've been thinking a lot recently is actually how satellites are actually operated. So when satellites are developed, there's usually a team of 10 to 12 full-time engineers whose only job is to hard code a bunch of heuristics of essentially edge cases and things that could potentially go wrong. And once the satellite is launched, there's people working 24/7 in tier 3 shifts who just have to monitor the satellite, look for any abnormalities, and try to develop fixes if something goes wrong. And I'm thinking, could we try to automate some part of this process away? Could we use AI to detect faults, but not only do the detection part, explain the faults to any operators, and also try to propose solutions? So for example, if one of your sensors starts failing, you could first detect that the sensor has failed, understand how it's going to impact the rest of the system, and then try to explain what's going on and develop a plan for the most optimal action to take so that the satellite can continue its operation. And I've been working on this for a little bit, but if anybody else is interested in the problem or has feedback for the idea, please come talk to me. I'd love to hear from you. Thank you.
Do you think I could just click on the drop down, right? All right, to open this up?
You want the first sound. That's possibly the one below you.
Oh, shit. Or I could just HDMI. Yeah, basically. Oh, sweet. Thank you. No? Oh, no. Okay. No, yeah, I'll just talk about it. Two projects I want to throw out there. One is for full flow combustion CFD. For the scope of this afternoon, we may not get to the CFD part, but 90% of the computation is just in the combustion part. So we can use a PINN and then do that. And then number two would be something with Q quantum and modeling a quantum tensor network to something like black holes and kind of explore that. Oh, this is unfortunate, but thank you.
Yeah, apologies on the connect. Guillermo, would you like to give a talk on ML cross physics for advancing non-invasive neurotechnology and brain-computer interfaces?
Is the presentation available or not? There's some useful stuff. So who here thinks would like to get some BCI but doesn't want to get a surgery right now? Okay, quite a few people. So yeah, I work on non-invasive BCI, exactly that. So, and I'm here because I believe there's a bunch of the bottlenecks for that technology specifically could really use the intersection of ML and physics. I work on using ultrasound for non-invasive BCI. Is this gonna show or not? So I work on using ultrasound for both reading and writing into the brain, and ultrasound interacts with the head and the tissues in your head in complicated ways, but there's a lot of reason to believe that you can use it if you focus it to write into the brain and in different ways to image your brain. But it's a very hard physics problem, but people are trying to solve it. And if you could see the images, one of the techniques that people are doing is they shoot ultrasound to your brain, and this is and they measure what's sort of received on the other side essentially. And this is framed as an inverse problem of trying to figure out okay, what's inside, given what sort of material properties inside could explain the sort of way the ultrasound has transmitted through your head. And this technology has been proposed as essentially being able to do the same thing that MRI can do, but way cheaper with a very simple device and way more scalable and portable, and it's basically all advantages. But it's a very hard physics problem, and it takes like at least like 12 hours or 24 hours to even solve it using some like gradient-based optimization. This is one of the areas in which I think like, yeah, this is kind of what I'm explaining. So imagine like MRI quality, but like at-home device that costs like hundreds of dollars rather than like millions of dollars. And like, by the way, this is like actually possible. Like we're working on that. So people are trying to find ways in which you can use like machine learning techniques where you take this sort of raw data and rather than like running the whole optimization problem, do in this case use an end-to-end like normalizing flow model to predict the structure in like much fewer computational steps, so they can become like much closer to real time rather than taking 24 hours. I'm just putting this here because I think there's probably way better like techniques to solve that than using like normalizing flows, and people are indeed like looking at how to use diffusion models for these kind of inverse problems. And it's actually like a very interesting theoretical area which will have direct applications to this. But like an even faster area is like you can use it for like the actual forward acoustic modeling rather than the inverse modeling. And I mentioned this here because there's a lot of other interesting approaches to working here, some of which I think are much more doable in like a hackathon, like in a shorter time frame, but they could still be like super powerful because even just the forward modeling of ultrasound going through your head, you know, like takes like a minute or something to solve, and like there's potentially like machine learning techniques to like make them like be way faster, and then you can like speed up like iteration development of this technology, and even use it like on device to like predict how to use ultrasound to like target different areas and stuff. There's indeed public database of like scanned brains of thousands of hundreds of them. And eventually this may even be used to like actually functionally image the brain to see what's neural activity is going on. So anyway, if you're interested in like solving BCI and doing that with cool like ML and physics problems, like talk to me.
Very, very cool. Okay, any last but not least lightning talks? James, are you trying to speak? Okay.
Okay, hey everyone, my name's James. I actually flew into the US for this event, so I'm representing the Wolfram Institute, and today I'd like to present an issue that is kind of like an open problem that I would love for some of you guys to potentially hack away at. What you see here in the background is a hypergraph rewriting system that's slowly evolving over time. And this is the foundation of what the Wolfram physics is based on. It's basically a state, which is the hypergraph, with an abstract rewriting system being applied to it. The limiting factor here is the scale at which you can do this. There's a combinatorial explosion when you try to apply certain types of rules to a state like this. It is hypothesized that if you are going to have a discrete version of physics, of space-time, that the discrete points there, the vertices and the nodes, are probably something like 10 to the 40 less than a Planck length. So scale is going to be very important to actually get to anything close to a particle, which is what we want to do, ultimately. I think using machine learning can help with that scaling. So somehow, instead of running the rules explicitly, maybe there's a machine learning model to extrapolate those and scale. And by the way, anyone who uses Wolfram language the best today will win the Wolfram Award, which is this rhombic hexacontiedron. So yes, that's an extra award I hope you don't mind me offering. Okay, thanks everyone.
Fantastic. And I guess as you guys know, we also have a sponsor, Anthropic, of this hackathon. So there will be $1,000 in credits to the top 3 prizes top 3 winners that come out of the event. So looking forward. I guess, okay, going once, going twice for lightning talks. All right. In that case, some final logistics. So currently you are sitting in a 4-story mansion. So feel free to use this floor, the floor below it, and the floor below that as open hacking area. There are people's rooms upstairs, so please refrain from going upstairs. There's a little sign, it says restricted area. Please respect it. If you're looking for the bathroom, there's a bathroom here and also on the very bottom floor. And finally, the Wi-Fi as AGI House, and AGI House is all you need. Raise your hand if you're not in the Slack. If you're not in the Slack. Okay, please find Senia as soon as this is over, so that we can head out. And yeah, I guess last but not least, physics hackathons are very rare. As far as I know, this is one of the first physics hackathons to exist. I think material science has been done before, but this is pretty special. So do take full advantage of this opportunity to create something fascinating, the intersection of AI and physics. There's lunch, as you can tell, sort of laid out for you, so do feel free to help yourself to food. And yeah, looking forward to seeing what everyone produces. Let the AI Physics Hackathon begin.
Can you repeat the Wi-Fi password? Attention is all you need. Attention is all you need. All lowercase.
Dude, they screened this premiere of the trailer for this technologist or something, and then this fucking clip ultra dramatic, playing the piano in your math jacket right here. This was at Heredicon. This was at Heredicon. They did like a trailer.
So wait, what is it from?
I put it in this chat. AGI House.
No, I saw a photo. I didn't see the actual.
No, it was a photo from this whole trailer, and there was like, they had like Beth, they had like, I don't know, it's kind of cool. They had Beth, they had Foresight, Allison Duncan, they had good people. They might be in it. Beth was like co-producer. Yeah, know about this? Some techno-optimist film? Dude, they were like interviewing you, they were talking to you, filming you, and then you were like, they showed you like playing the piano all dramatically, and it was hilarious. It was like, yeah, a bunch of people saw it.
You don't have a link.
I don't know, I can find it. It wasn't on YouTube, it was like a private little trailer. It was hilarious. So look, anyway, Defense Tech Hackathon, we got momentum. Thanks for coming together nicely. We were visiting a place today, and we're gonna make a floor plan, a bunch of shit. We're gonna do a bunch of remote boundaries, whatever. If you're down, like at the end of the day, if you can help us get this, get the engineering talent, filter, and then like, if you wanted to do like the whole like LCM thing, Make a new one, make different ticket types. Or just come from the hardware studio. And so you're going to have a few different spectators. And then it just gives you access to really good font definition
And then we also want to
That event I consider now to be sale. I'm not registered. And it was going to be, August, super cheap and it was way back. And so I think
Oh,